Good afternoon. This is CIVE632, Computational Hydraulics and Hydrology. Today is September 20th, and this is the beginning of the 5th week of this class, fall semester here at San Diego State. The subject today is a paper that I wrote in 1991, I believe. And this is such an important paper, and it's so detailed that I think I may well end up spending the entire session on it. So let me first, before I go any further, I'm going to share the screen. Let me see. Right. Okay. Can you guys see the green page?
Yes.
Okay, cool. Okay. So there's a story behind this paper, which is an interesting story. You would recall that the kinematic wave was found by accident by Seddon in the year 1900. He didn't call it kinematic wave, but he was talking about the kinematic wave, about the concept that there's a celerity and that the celerity is a constant celerity, meaning that the waves have a way of not attenuating. They don't dissipate, they stay there, and they have a celerity which can be measured. That's what Seddon did in the year 1900. But we have to wait until the year 1955 for the British Leahy and Whittam to write a paper on the theory and to give it a name, to call it the kinematic wave. Okay, so then you have several other actors, some of which are most important are Doug and Will Heiser and myself. Why not say it? 1977, what I call my S paper. Well, turns out that in the year 1988, there was a paper that was published in the hydraulic division. Okay, and I'm going to read from our paper. There's a continuing controversy regarding the nature and applicability of the kinematic wave. Researchers and practitioners alike have reported successes and failures of the model, with papers continuing to appear in the literature describing what the model can and cannot do. Now, there's a paper by Hromadka and De Vries, 1988. And to be honest with you, well, let me just say at this point, let's go to Hromadka and De Vries. What's the reference in here? Hromadka and De Vries, Kinematic Wave and Computational Error is the paper by Hromadka and De Vries. Now, you already know that the kinematic wave has an error. And with that error, it ends up being really a diffusion wave. So if it has the error, it shouldn't be called kinematic wave. However, like I said, there was a confusion and controversy. And in 1988, these two people, which are well known in the field, Hromadka is a very well-known consultant at the time, 1988, and even to this date, I believe he's still practicing. De Vries, also a very well-known gentleman, and they kind of endeavored to write about the error of the kinematic wave. So I thought that that perhaps that was a mistake and there was some confusion. At the same time, once they published their paper, there was a period for discussion. That's normal in all journals. All reputable journals have a discussion of 6 months. So there were 5 discussions. The discussions were by Doughty, who also is a well-recognized hydrologist at the time. I'm talking about 1990 here. Goldman, who works with or used to work. I'm not sure where Goldman is right now, but he used to work with H.E.C. Davis. Hromadka and De Vries, they also did a closure because the author does a closure. Merkel, who is my friend, my associate, Merkel is the guy that first gave to the world our linear diffusion model. We wrote a paper or did some work for SES, and Merkel was representing SES at the time. So he came out in 1990 knowledgeable about the kinematic wave and its diffusion. Ulrich and Woolheiser, I don't know about Ungrich, but Woolheiser, um, we know Dave Woolheiser very well. He used to work for many years for ARS, the Agricultural Research Service. And Woolheiser managed to write two discussions in there. I don't know how people do that. You write one discussion with one author, I guess, I don't know. I'm not going to second guess these guys, but you can see the record. Woolheiser and Goodrich. So Woolheiser wrote two discussions in relation to the paper written by Hromadka and De Vries. So I, at the time, was thinking about this, and I said to myself, somebody's got to straighten these guys out, or this guy out in particular, meaning Hromadka and De Vries, because the other four people, five people, try to put their 2 cents worth into the issue. So I decided I was going to wait and I was going to write a paper afterwards. So after the discussion period was finished in 1990 and the closures were, or rather the discussions and the closure were published, I wrote this paper. And it is a review paper. Now, I think I already mentioned to you that you don't write a review paper if you're nobody. But at the time, I felt that I was no longer a nobody. It was 1990. It was not 1975, right? It was 15 years, and the Army Corps knew me very well. SCS knew me very well. So I wrote this paper trying to straighten out the mess, because it was a mess, in my opinion. Okay, so I titled it The Kinematic Way Controversy. And then the issue later on was whether indeed there was or not a controversy. And I wrote it and I titled the controversy because I thought that even up to 1990, there was a controversy. People did not understand the true behavior, the true capability of the kinematic wave. And I can expound in all sorts of stories, but I'm not going to waste your time on it because we have a lot of experience on this subject and a lot of stories with it. Okay, so current areas of concern focus on the following issues: whether the kinematic wave can describe physical diffusion, and if so, under what circumstances. That's very important because the Army Corps had already messed up in the 80s when they talked about the diffusion of the kinematic wave. The kinematic wave is not supposed to have diffusion. If it does diffusion, then it is already a diffusion wave or diffusive wave. The Army Corps was wrong at the beginning of the 80s, but they later on fixed themselves up. Okay. Second, whether the kinematic wave can eventually replace other well-established methods of surface runoff generation, such as the unit hydrograph. So here we go. How are you going to generate a hydrograph in hydrology? Since 1889, we were generated with a rational method, but the method does not give you a complete hydrograph. It just gives you a peak flow. And then you have to fill in the hydrograph, assuming, of course, that the time base is double the time to peak, etc. It's an isosceles triangle. But that was 1889. Now, Sherman in 1932 felt that he could not design the dams that he was designing with the rational method only because the rational method was very restricted to very small basins. Later on, defined as 1 square mile. And Sherman was looking at 5,000, 3,000 square miles. So he derived the unit hydrograph, which is a linear theory to, I don't know how much you guys know about the unit hydrographs. This is not our topic now. That topic we cover in surface water. But the unit hydrograph was developed in 1932, and it basically was enable us to apply hydrology to a much larger basin than the rational method. But the Army Corps put those two hydrographs or two methods in HMS first in HEC1, and then it's sequel, which is HMS. And they said, well, if you want to use unit hydrograph, I'm sorry, not the rational method. They put the overland flow, and therefore they gave us the chance to use either overland flow or unit hydrograph. So the question then is whether the kinematic wave, as in a calculation of overland flow, which we are going to do this week and next week, can eventually replace other well-established methods of surface runoff generation, such as the unit hydrograph. In other words, the issue here was, are they competing? Are they complementary? Or what? Because you guys had the chance of use either or as parts of the map of the model HMS. And thirdly, whether the kinematic shock is as common in practice as calculations would seem to indicate. And here we go. The kinematic shock was first measured by Lahir and Whittam in 1955. It was documented by Woolheiser in his early work in the 60s at Cornell. Kibler wrote his thesis in 1970 at Colorado State on the kinematic shock, the kinematic wave and the kinematic shock, extensively studied. So then the question was, and has been posed it was posed at the time in many places, is to whether the kinematic shock does exist. Or if it does not, if it exists, is it as common as calculations would imply that it is? So those were the three issues that I set out to address in this paper. In addition to that, I put in there some other issues, but these are the three major issues that I'm going to discuss here. Then I say, answers to these questions can be found in the literature, but they are dispersed. This difficulty appears to be fueling the current controversy. Therefore, the aim of the present paper is to review the concept of kinematic wave, delineate its range of applicability, because Woolheiser had delineated the range of applicability, but they did it only for the overland. They did not do it for the river flow. I did it for the river flow, but we need to come out and stress it again, because things become popular or common through repetition. We know that for a fact. Critically examine its overall modeling philosophy, meaning what exactly is the kinematic wave? I mean, like I said, I can tell you stories. I was writing papers at the time, and I was getting all kinds of comments in the comments from the reviewers, because as you know, when you write a paper, you submit yourself with 3 referees, and they are blind. You don't know who they are. They know who you are, but you don't. And they're typically either applaud you and say, hey, it's a great paper, or they say, no, it has some bugs, you can fix them, or outright say it's not a good paper, so I decline the paper. So sometimes you have your papers declined, you know. And to the extent that some people have good batting average, like I would have maybe 70%, which is good. In other words, 7 out of 10 papers that I wrote got published. Okay? So we say in here, it is hoped that this review will help focus the attention of researchers and practitioners so that the controversy may be brought to a timely end. And I do believe that we did bring the controversy to a timely end. I didn't hear anything else about the questions about the kinematic wave. Why? Because we came out so strongly and so clearly on this subject, as you will see. I've been told many times that this paper is very clear. So the concept of kinematic wave, on the subjects that I've already covered, I'm going to go through quickly. Others that I have not covered, I will stress at this point. So the concept of kinematic wave is well established. In contrast to the dynamic wave, which features a significant inertial component, a kinematic wave is one in which the inertial component is too small to be of any practical importance. That's true. We know that. So in other words, a kinematic wave exists only because the inertial component is small. Does the inertial component, is it small or is it large? And the answer is typically it's very small. That's why we have kinematic waves. And diffusion wave sits in the middle of it. So if the wave is barely not kinematic, it could still be diffusive and yet not be dynamic. So that's the idea. So there's three major classifications, or classifications into 3 major waves in here in open channel flow. A second, less restrictive type can be formulated by neglecting the local inertia, convective inertia, and momentum source terms, but keeping the pressure gradient term. The momentum source term is the term on the lateral inflow, by the way, which we will get into more detail later on. Keeping the pressure gradient term, and that was Hayami's invention. Hayami said, we don't need to go with the inertia. We're gonna drop both inertias and the pressure gradient and end up with. I'm sorry, Hayami said we're gonna drop the inertia. I'm sorry, inertia, but not the pressure gradient. So then we end up with the Hayami analogy or diffusion analogy of Hayami. To avoid confusion between these two types of kinematic waves, so we really call both of them kinematic, meaning no inertia. But one of them is kinematic wave proper, and the second is a diffusion wave. Conge, I believe, was the first one to come up with the diffusion wave, not with the name of diffusion wave. But he did not publish it extensively. So then several years later, he did this in 1973. And 4 years later, when we came out and wrote our S paper, we came at it as diffusion wave. We called it diffusion wave. And our name finally stuck. So I guess you could say that Professor Ponce could be credited with being the person that introduced the diffusion wave as a name into the literature. At the time, there were other people that were calling the same concept different things. And that usually happens at the beginning of something new. The name zero inertia comes to my mind. In fact, the diffusion wave has zero inertia. But why call it zero inertia when you could call it diffusion wave? Or you could argue the opposite. But the point is, which name is going to stick? And basically, the name of diffusion wave stuck at the time. There was a fight in the late 80s whether they should be called diffusion wave or zero inertia wave. I can mention names of people that were defending or arguing that the name should be zero inertia, but the matter has already been settled. Now, the kinematic wave assumption assumes to substituting a uniform flow formula for the equation of motion. In other words, you're going to say the equation of motion, well, I don't want to consider all the terms. I'll just say that the equation of motion is uniform flow. So in other words, you're saying that there's no forces in the momentum. The momentum balance has no unbalanced forces, just two forces, gravity and friction. So in essence, it says that as far as momentum is concerned, the flow can be steady. The unsteadiness of the phenomenon, however, is preserved to the rate of rise of the continuity equation. So the formula, or rather the formulation, is still unsteady, but it is unsteady due to mass, not to momentum. And this is what led Leggett and Whittam to call this wave kinematic, because it was obviously not related to unbalanced forces. And you know, kinematics is not related to unbalanced forces. So the name kinematic stuck after Leggett and Whittam decided to call it that in 1955. Now, whether we can or cannot consider the momentum, as I say in here, this can be reconciled with reality only if the flow unsteadiness is very mild. That is, if the changes in momentum are indeed negligible compared to the forces driving the steady component of the flow. So the unsteadiness is very mild, you can call it kinematic. If it's very, very mild, then the flow will not diffuse. And that's it. We already know that. We repeated this in many ways. What is the equation for the kinematic wave? Is this equation, which we have already presented to you. It's in Leggett and Whittam's paper, it's in Conge's paper, albeit with different notation, which is unfortunate, but that's just the way it is. We got to get used to that. Notice that in here, we have a C which affects the lateral inflow. So this adds the equation with lateral inflow. The C is the set celerity, and the Q sub L is the lateral inflow. And the units have to be maintained, by the way. These are all physically homogeneous equations. Now, this equation 1 is for flow, for channel flow. But if we use it in overland flow, then we gotta call the uppercase Q, we gotta call it lowercase q, and then you have to change the equation a little bit. And equation 2 is the one that is applied for in terms of unit width discharge, and that's the one that applies for overland flow. Because what has happened in practice is that overland flow has been solved with kinematic wave, starting with the work of Woolheiser and Wooding and Shockey. Remember, I mentioned that to you in the middle 60s. So at the beginning, the task of modeling overland flow was done with kinematic waves. That was through the 60s. However, now we have done it with diffusion waves. We did that in 1986 for the first time in a paper that I wrote at the time and that we will have a chance to read hopefully next week in much detail. Okay, so that's the story or the history on that. The kinematic wave celerity is defined as the slope of the radiant curve. We already know that. It's been hammered to us for several times already. And celerity equal to QdA, that's the celerity of Seddon, expressed in three ways. You can express it in Q and A, or you can express it as Q and T. No, Q and Y, 1 over T dQ dy. Or you could also express it as beta U, or beta times Q over A. Those three ways, actually 4 ways, you can see another formula in there, is various ways that we could express the kinematic wave with specific applications to specific problems. Equation 1 and 2 is a differential equation of first order. Therefore, it can describe convection or advection, but not diffusion, which is a second order process. That we should know from math. In practice, this means that the kinematic wave equation can describe the travel of a flood wave, but not its attenuation. Although equation 1 cannot describe diffusion, it is a quasi-linear equation because the kinematic wave celerity is a function of discharge. In other words, right here in equation 1, the C in the second term is a function of Q. So that's what we refer to this equation as quasi-linear. Okay? If C would be like C squared instead of C, then it would be nonlinear. Definitely. But that's not the case. It's quasi-linear, almost linear. Okay. The quasi-linearity gives kinematic waves the property or the tendency to change in shape. So there's two things in here. One is whether it attenuates or not. And the answer we already said, if it's kinematic, it will not attenuate. If it's diffusive, it will. But then there's another issue, the nonlinearity. Will it change in shape? And the answer is yes, it will change in shape. So then the question is here, from a practical standpoint, if the kinematic wave changes in shape and diffuses, it will lose itself, meaning it will diffuse eventually, and the diffusion will counteract the steepening. Always, diffusion counteracts steepening. Now, if it doesn't diffuse, then it can steepen, and it can become eventually a killer wave. It will kill people. The problem is that in order to do that, it has to the steepening has to be very sudden, or it has to develop through a long channel. And the long channels are typically not there. So the killer wave is an unusual situation. It has been documented in places around the world. Certainly here in the United States, we had the case of the Tanque Verde Creek in Arizona, 1982, that killed 8 people. That has been documented by Hjalmarsson, working with USGS. So kinematic wave solutions can be attempted in a variety of ways. Analytical solutions are possible. These are the solutions presented by Doug in his work that we have already read. These solutions describe the convection of a flow quantity with the celerity C in the absence of diffusion. Numerical solutions are possible using the method of characteristics or the finite difference methods. Now, in the history of numerical hydrology or hydraulics, it's the same. It's basically the same. We don't make a distinction here. The method of characteristics is the old method, the granddaddy, so to speak. It was developed in the 60s. It was applied by Abbott, the great British gentleman, considered to be the father of numerical hydraulics, Abbott, Michael Abbott. He came out with a book in the middle 60s on the method of characteristics applied to hydrology. But subsequently, his work was superseded because turned out that the finite difference equation was better, more practical. People liked more the finite difference. It was more intuitive. So by the 70s, Abbott's method of characteristics was basically out of place. I remember Fred Thur, my friend Fred Thur, wrote a dissertation on the method of characteristics, presumably the last dissertation ever written on the method of characteristics. Not to say anything about Fred, he's a very good friend of mine. That's what he ended up doing. Okay. In Overland Flow, the nonlinearity of the phenomenon usually leads to wave steepening and the eventual development of a shock, which was discovered by Woolheiser and Kibler. Kibler was working under Woolheiser. They did a complete study of the kinematic shock. What is the kinematic shock? A kinematic shock is a kinematic wave that has steepened to the point where its rising limb has an almost vertical face, wherein the flow develops a singularity and loses its gradually varied property. So at that point, you can't even calculate, because you can't calculate when the flow changes from 1 to 2 or to 3 or to 5 inside the cell size. It's impossible to pick up, right? At that point, the whole thing will go bananas. It will go wacko. I mean, it will become a problem of computation. That is a problem that Woolheiser in particular faced when he was doing his work. How to handle, how to figure out what to do with the shock if it ever presented itself. Of course, there's a lot of things they didn't know at the time, but we decided in the 80s that we were going to settle this issue, and we did, and I'll get there eventually. Numerical diffusion and dispersion. I'm going to try to speed up here, otherwise we will not finish. We already heard about numerical diffusion and dispersion. We heard about amplitude and phase portraits for convection problems. They were presented for the first time by Conge, albeit in an incomplete fashion, not 100% correct. And then we did it in 79, and then subsequently in the year 2016 with the work of Vavia, we put it in a calculator, and now at this point, the issue of amplitude and phase portraits of the Muskingum Conge has been settled. Okay, finite difference solutions exhibit varying amounts of numerical diffusion and dispersion. Fully centered schemes are of second order. Here is interesting. Here, pay attention to what I'm going to say. Fully centered schemes are of second order, exhibiting no numerical diffusion. However, these schemes may exhibit numerical dispersion for Courant numbers other than 1. And that's the reason why we stress that the Courant number has to be 1, because by doing that, you solve the problem. What exactly is the requirement that Courant number be equal to 1? Okay, I'm going to try to explain it here. I don't have a blackboard to explain, but I'm just going to tell you off the bat. The problem is that when the Courant number is equal to 1, the characteristic of Abbott runs exactly through the cell. It's like you're shooting and you got a way to shoot. If you're shooting an animal, if you had eyesight, you can shoot better, right? So for Courant numbers equal to 1, you can get at the answer very quickly. If the Courant number is 2 or 3, then it deviates. It either goes up or goes down. The rectangle of computation, the grid or the mesh of computation, it goes either too tall or too wide, and it has a tendency to miss the computation. That's exactly what is happening. Now we know the definition of the Courant number is the ratio of the physical celerity to the grid celerity, dx of delta t. Off-center schemes are of first order. Second order is better than first order. Yes, but to an extent. Sometimes You have to go first order because first order may not have instabilities, while second order can have instabilities. And you want to first get rid of the instabilities and then look at the convergence. That's the way the procedure. You cannot get rid of the convergence and then look at the instability. It's like, how can I say, it's trying to solve a minor problem after you have attempted the big problem. At any rate, first you handle the instability or stability, and then you go to the convergence. And we realized that, of course, if the system is off center, then there will be problems. Let me also say at this point, because this is at the source of the so-called controversy, because Conch came up with this theory, which is a good theory, okay? And he basically was saying, let's dump the convex method because it's no good. It will give you any answer that you want. As a matter of fact, it gives the answer that you don't want. He didn't say it, but he implied it very strongly. That was 1969. In 1988, 19 years later, Chromatka and De Vries came out defending the convex method, saying, in no uncertain terms, that, they were about the same. The accuracy is the same. Muskingum-Conch kinematic wave is the same as convex. That is incorrect. And that's the way we decided to write this paper. And we did write it. We did finish it to settle the issue. There is no way for the convex method to be comparable to the accuracy of the Muskingum-Conch, or even the kinematic wave, because the kinematic wave is physically based. It may have drawbacks, but it's physically based. The convex method was not physically based. The convex method was developed by Marcus in the year prior to the year 1954, because they had to come up with some routing method for the manual, for the NEH4 manual. And I guess I wasn't there. They gave it to Marcus. Marcus was a miracle worker. He had developed a runoff curve number. So I bet his bosses said, okay, Vic, you're going to give us a routing method. And Marcus had no knowledge of math. And therefore he came up with something very simple, but it was empirical. It was the convex method, which of course was superseded. I should tell you in repetition that when Fred Thur went back to SCS in the year 1976, he told them that the convex method was flawed and that they had to retire it. And Fred was a very gun-ho guy. He did convince his bosses to retire the convex method. And that's when they came up with the Atkins solution, which was kind of piecemeal half of the way. That's when they ran into problems, then they listened to me when I said that you could have a better solution. Now, numerical diffusion arises due to the neglect of the second order term. Numerical dispersion arises due to the neglect of the third order term of the Taylor series expansion. Here we go with the findings of Conch as well as Frederick, who came in later. Therefore, in a typical application, numerical diffusion is about an order of magnitude greater than numerical dispersion. That's true. Second order, third order, fourth order. The fourth order is very small. I already said the other day that Duke had come out with four order terms. Remember the fourth order moments or cumulants, as he called it, cumulants? That, in my experience, has not been used in practice. Not even the third order has been used in practice. So Duke was theoretizing, as you could say, talking theory, and it is nice to talk theory, but the practice is not there, even to this date. And he wrote those papers 40, 50 years ago. Okay. Carried to a practical limit, the fact that the diffusion is artificial, the numerical diffusion is artificial. And it is intrinsically related to the grid size, can be readily demonstrated by solving the same problem several times, each time having the spatial and temporal increments. So in other words, the increment is 100 feet, then you do 50 feet, 25 feet, 2.5 feet, 6.5, 6 feet. Carried to the practical limit, this test will eventually lead to the eventual disappearance of the numerical diffusion, with the result approaching the analytical solution of the kinematic wave. We did that in the year 1986 to prove that the kinematic wave was off because we had to compare the kinematic wave with the diffusion wave for the overland flow problem. And the Army Corps was using the kinematic wave, and they had not used the diffusion wave. So I had to come up with a way of showing to them that here it is, here are the calculations. You guys could repeat what I'm doing. And I guess they did it. Because I said the kinematic wave numerical diffusion will vanish if you consistently and repeatedly decrease the size of the grid. Well, the Muskingum Conch was grid independent. Remember, we talked about that already. Okay. Since diffusion and dispersion are inherent in the choice of space and time steps, the result of a finite difference solution is perforce grid independent. In other words, a finite different solution of equation kinematic wave is grid independent. The calculated runoff varies with the choice of grid size. More so because of the fact that we, in the kinematic wave solution, we never told them about the diffusion of Hayami. So if there is diffusion of Hayami, then the kinematic wave will not solve it. Kinematic wave is giving you an answer, but it's not the right answer because you were never able to. You did never tie that answer with the physical diffusion, which is the correct answer, is the physical diffusion of Hayami. I come a little bit strong in here. Then I say it's pointless to try to calibrate a kinematic wave by varying a physical parameter such as Manning in order to match calculated results. People were doing that at the time. That was Mr. Chromatka. I'm sorry. That's a good friend of, well, not a good, he's an acquaintance. That's what they were doing. They were trying to calibrate the kinematic wave grid against the N. And you can do that forever and never get it the right answer. Okay, diffusion wave modeling. Now we go to the next step. Diffusion wave modeling, we already know the contributions of Conch, the contribution of Hayami. Now, I checked. Conch had 4 references in his paper in 1969. None of them was Hayami. I am given to understand that Conch was not aware of the work of Hayami. But that's just a speculation of my part. And my speculation is based on the fact that he did not mention Hayami. Because normally, if you're a scientist that I guess, what's the word, serious about this, you do research. When you publish a paper, you have to put in the paper all the previous work that was done. First of all, because you don't want to come up with something that has already been done. And second, we want to recognize the work of scientists, right? That's all the payment that scientists have, the recognition of their work, mentioned whenever there's a citation later on. But Conch didn't do it. So I'm going to say that at this point that he was at the time not aware that the diffusion wave had already been treated by Hayami 18 years earlier. But these equations are of Conch and are of Hayami. And the equation 5 is the diffusivity of Hayami. The diffusion wave equation can be solved analytically. Yes, we can use Hayami's diffusion analogy, which I never actually touched, or analytically, or numerically with the aid of a scheme for parabolic equations. Now, if we're all good with numerical methods, there's numerical schemes for parabolic equations, which put into diffusion. And for instance, the so-called Crank-Nicholson scheme. So it's one way of doing it. However, that is not the preferred way. Why? Because it uses 6 points, not 4, and people don't like that. You use 6 points because it has 2 terms. The diffusion is not brought in after the fact like Conch does. The diffusion is brought in at the beginning, like solving numerically what Hayami had proposed. Hayami never proposed to do a numerical method. He did an analytic method. But by the time you get to the numerical method, the only way you could do it is by using the 6-point Crank-Nicholson scheme. But that's all because it's not done by in practice anymore. An alternative is to extend the finite difference solution to the realm of diffusion waves by matching physical and numerical diffusivities, which is what Conch did. The physical diffusivity is the hydraulic diffusivity, and the numerical diffusivity is the numerical diffusion coefficient of the discretized kinematic wave model. That is the coefficient of the leading second-order term. When the Muskingum scheme is used to model the kinematic wave, this method is referred to as Muskingum-Kunch, starting with the work of Price, 1975. The Muskingum-Kunch has a significant advantage over kinematic waves of being essentially grid independent. The question of grid independence has not been mentioned a lot in the literature. People just do the models and they don't test grid independence. In my mind, the first thing you need to do is to test grid independence. Once you test grid independence, first stability, then grid independence, which guarantees convergence. So therefore, then the method is good. Never mind that you still have to guess on the parameters like the Manning's N and the cross sections and this and that. The cross sections you can measure, but you will be unable to measure all the cross sections. So you have to do a little bit of fuzziness in there in the data. Now with the tools that we currently have, GIS and DTMs and so forth, a better job could be done. But there's still some room for fuzziness, like I already told you the other day, the contribution of the lateral inflow, which is largely cannot be tracked down. Really cannot be tracked down. And there is contributions of lateral inflow. There's two contributions. The positive contribution in the wet areas where water is coming out of the ground is base flow. Now, typically the defense against that is that you're not calculating the base flow because you're calculating the flood, and the base flow is not floods. But if you're in the middle of something, like it's not too dry or too wet, then you're in the middle, then you got to consider it. Another situation is when you have routing over an ephemeral stream, which has no flow. At that point, the water is going to immerse itself into the ground. And then eventually you're going to lose the flow. So you got to figure it out what is going to be the so-called transmission losses. SCS calls it the transmission losses. While you transmit the flood, it will lose itself. Has this happened? Can this be done? Yes, of course. There are situations in Arizona where routings have been done where you start with, say, 100 and 50 miles on the road, you got nothing. So you disappeared. The flood disappeared. Where did it go? To the groundwater. Really? How could that happen? Yes, it does. The ephemeral streams are the means of recharging the groundwater when you have a flood. So we know that. Applicability. Wilheiser came up with this famous equation. But note, as I've said earlier, that the equation 6 is only for planes. The LCVO is the length of the overland flow plane. Wilheiser did not consider the wavelength of the flood or the period of the flood. Why? Because they were looking at short planes. And in a short plane, you cannot look at the period. The period is going to be overwhelmed. Rather, the length is going to be overwhelmed by the period. The period is going to be much longer. So there's no, if you're looking at the applicability of the kinematic wave, there's no point to look at the period or the wavelength. However, we were not looking at the applicability of the overland flow problem because when we did this work on the S-curve, we were looking at channel flow, not overland flow. So we gave up the LCVO and call it an L, which is the wavelength and its corresponding wave period. So ours is for the wavelength, rather not for the wavelength. Ours is for the channel. And we came up with equation 7. Equation 7 for the kinematic wave and equation 8 for the diffusion wave. Now, Wilheiser had not come up with the diffusion wave. As a matter of fact, Wilheiser never studied the diffusion wave. They somehow got the kinematic wave. Why? The answer is because they were looking at overland flow, and at the beginning, overland flow was defined as steep channel, or rather steep plane. What is steep? 1%. If it's 1%, it's already kinematic. So he never had to worry about the slope of the plane being less than 1%. But in general, if you have a slope of 1% or 0.5% or even 0.1%, then you're already in the diffusion realm, and you would have to calculate the Muskingum-Kunch instead of the kinematic. As to whether the planes in reality are not 1% or 0.1%, that would depend on the practice. If you go to Florida, yes. If you're here in San Diego, probably not. You know, we have a lot of valleys and canyons and so forth. Florida is very flat. Other places in the US could be flat. Um, it depends on the terrain and the geomorphology of the terrain. But in general, it is better to do the calculation with the Muskingum-Ganj. Why? Because the Muskingum-Ganj will solve in one whack any slope. You won't have to say, oh, steep slope, mild slope, whatever. No, any slope will be calculated by the Muskingum-Ganj. And we have shown that to be the case. That's a paper we wrote in 1986. Okay. Overland flow versus unit hydrograph. This is very fascinating, actually. Let me see how large this article is. Okay, not that much. Okay, we're progressing very well in here. Okay, so then the question is, unit hydrograph, 1932, Sherman. Overland flow, 1965, Shackey, Wooding, Woolheiser. That's 30 years later. Why? Because the unit hydrograph was done by hand, while the overland flow was done with a computer. We had to wait until the computer was here in order to do the calculation. The overland flow is distributed. You get any answer anywhere, while the unit hydrograph is one answer. You get a whole basin, you get one answer at the end. You cannot ask the unit hydrograph to develop a hydrograph or a unit hydrograph, for that matter, at a point, some point inside the basin. No, it doesn't happen. This is lumped, only one answer. What you could, though, do is to consider the basin formed of many sub-basins. But if you do that, then you have to have a network. The basins are not just flying out there. They are networked. And if you have a network, you have to have a topology, which is in a mathematical problem, much different than hydrology, right? There is a incipient topology. I say incipient because HMS is an incipient topology. We have developed watershed models and we have advanced topologies, but it doesn't matter because you're not going to use our models. You're going to use HMS, right or wrong, because that's just the way the ball bounces. Okay? We've used our model, but in only specific cases, you know, there was not a general case. I have to be realistic about this. Okay, so what is the issue then? Overland flow versus unit hydrograph. Okay, the overland flow is well known to be applied when you can discretize the medium or the watershed. So that off the bat would tell us that if the watershed is at 5,000 square miles, like Sherman used, you're not going to be able to do the overland flow because it's just too much data. Where are you going to do the data? And therefore, then it follows that the overland flow would be applicable to the smaller basins. And for the larger basins, you would have to have the unit hydrograph plus routing if necessary with the concept of the network. So that's one thing. Now, what in the middle? What happens in the middle? What happens if you have a basin like it's a couple square miles and you feel like you got all the data and you can do the calculation with both? At that point, you're on your own because you're going to do a calculation with the overland flow, you're going to do a calculation with the unit hydrograph, and they're going to be different. They are going to be different. And there's nothing you could do to change that. You could calibrate the thing and make them the same, but that's not really the correct procedure, right? So therefore, you have to basically play with a grain of salt. I'm going to use overland flow, fine, or I'm going to use unit hydrograph. The issues, these two things are so different, they're really not comparable because the overland flow gives you a ton of answers, more answers that you would care to use. The unit hydrograph gives you only one answer. So if you want to use 2 or 3 or 5, you're stuck. You can only use only one answer. So those are the limitations of these things. But nevertheless, these are the two methods that we use, that we currently use. People use overland flow or the unit hydrograph. Okay? In contrast to the kinematic wave, the unit hydrograph is a conceptual model, lumped, spatially lumped, and based exclusively on hydrologic data. Although originally derived for large catchments, the method has been found to have primary applicability to mid-sized catchments. Because the reason why, I think I already told you that, the reason why Sherman used his unit hydrograph theory with a large catchment is because at the time when he was doing this, there were no networks. It was all done for mid-sized or large catchments. And that's what he was doing anyway. He was doing the hydrologic calculations for large dams. And there he was a consultant. So therefore, 5,000 miles was not uncommon for Sherman. Nowadays, we would a little bit have to think twice before we apply the unit hydrograph for Sherman in one whack to 5,000 miles. That probably would be malpractice. They would say, hey, you cannot do that. You got to do it in several instances with watershed and so forth. Using HMS, set up your watershed, your basin, and so forth. Okay. Since the overland flow is applicable to small catchments and the unit hydrograph is applicable to mid-sized and large catchments, it seems that there should be very little overlap. Okay. In practice, however, both models provide, HEC1, which is HMS, the current HMS, provides users with a choice between these two methods to solve any runoff problem, regardless of scale. This raises the question of which method is better. The methods are such different nature and have such different data needs that they're not comparable as apples and oranges. Perhaps the only defensible argument in this regard is that the kinematic wave should increase in accuracy as the catchment decreases. The unit hydrograph should increase in practicality as the catchment increases. Specific comparisons between the two methods are likely to lead to heated arguments. That is correct. But the central issue of accuracy is not likely to be settled. For one thing, the overland flow kinematic solution is based on our current imperfect knowledge of friction mechanisms, including the estimation of Manning-Sen and of the rating exponent describing the mixed laminar turbulent regime. What the heck does this mean in short words? It means that we do not have a friction predictor if the flow is mixed. If the flow is turbulent, we got Manning. If the flow is laminar, we got turbulent flow, Izzard solution, the Izzard type solution. But if it's mixed, as with Horton, with the M or the exponent equal to, you're out of luck. You could use Manning, but it's forcing it because you don't have an equation. And most people don't understand what I'm saying in here, by the way. They still believe blindly on the Manning equation to solve all kinds of problems in the overland flow. But that's not true. It would only solve the beta equal 5/3 correctly. Likewise, the unit hydrograph would have to be verified with concurrent rainfall data, which is not readily available for the typical mid-sized catchment. Keeping in mind the question of scale, the kinematic wave solution does have the significant advantage that it can describe spatial and temporal rainfall, which the unit hydrograph cannot do. Therefore, in situations where the scale can be reasonably compromised, the overland flow should provide better detail in the simulation of flat flows. And that's the way we understand it. The overland flow does provide better detail. However, it does have a drawback. The overland flow is usually done in an open book, and the open book typically doesn't exist. What exists is something central. Yet we have been able to live with the open book for 50 years, and I do not think that in practice we're going to improve that. There is a slight variation in there. Okay. And here I do my 2 cents worth in here. There's an urgent need to develop synthetic unit hydrographs that reach beyond established practice. The Snyder Hydrograph was done in 1937 to do Corps of Engineers practice. The SES dimensionless 1955, they kind of competed with each other. We know now that the SES applies for small basins, which is those that the SES was interested in, while the Snyder applies for larger basins for which the Corps would be interested in. Why is that? Because the Corps has larger basins. The Corps has basins which could be 1,000 square miles. SES is not in the business of analyzing 1,000 square miles because they were told by Congress that they should work the upland, the headwaters, control the soil in the headwaters. You have no business downstream. That's the Corps' business, the flood, the big flood, not the little flood. So that's the difference between soil conservation and Snyder. Now, what about I'm sorry, soil conservation and the Army Corps. Now, what about the Bureau? The Bureau came in there thirdly, and they said, well, we got large basins, so they developed their own. That's been treated in chapter 14 of my blue book, the USBR unit hydrographs. But they're empirical. They're empirical, so I mean, you have to downgrade it a little bit because of their empiricism. In other words, they did six unit hydrographs for different regions in the United States. They divided the 11 Western United States into 6 regions, mountains, this and that, according to geomorphology, of course, because geomorphology is the important problem here. That's what we're modeling, geomorphology with numbers. So they divided into 6 regions and came up with 6 unit hydrographs, and there is it. I would venture to say that those hydrographs are not very much used. They would be used by those people that are consulting or working with the Bureau of Rec, and that they are requested to use, and then they can do it. But if you're not consulting or working with or for the Bureau of Rec, you're not going to use it because it's not. There are many other ways to do it, particularly the Army Corps. You know that the agencies compete among themselves. The water agency, there's about 5 or 6 agencies in the United States, water-related agencies, and they compete among themselves. And actually, right now, the Army Corps of Engineers is kind of the leading water agency because of the Heck Davis lab. The Heck lab at Davis, I'm sorry, because it's very prominent, because they've got the HMS, the Heck RAS, and so forth. They have other labs, but they're not as famous, or I guess you could say useful for us. Like the Krell lab that I already told you, Ferrick worked at the Krell lab, that's for cold regions. And the lab at Vicksburg, though they used to do physical models. Since hardly anybody's doing physical models anymore, I honestly wonder, I hope they're not listening to me right now. I'm wondering what they're doing out there at Army Corps lab at Vicksburg. Well-known lab in the 40s, 30s, 20s, 60s, 70s, but not anymore. They're not very well known in this area. Kinematic shock. The kinematic shock was discussed by Lahir and Whittam. The shock arises to the nonlinear feature, which under the right set of circumstances can result in a kinematic wave steepening to the point where it becomes a wall of water. The shock is a direct consequence of the nonlinear steepening. Okay, so what are we doing here? We were concerned about the kinematic shock. Remember, I talked to you the other day and I said when I was in the Pantanal, I told Hugo Benito that I wanted to see the steepening of the waves, and he told me point blank, there's no wave steepening here in the Pantanal. And I understood that he was correct because he was a serious professional. If there were some steepening over any reason for doubt, he would have not said that. And he was correct. Okay, then later I came back to San Diego and I said, this is an interesting problem that people don't know about, so I'm going to research it. Sure enough, there was Diane Windingland came to me in the year 1983, I believe, and she said, Professor Ponce, I'm an undergrad. I'm going to finish in a year or so, but I want to do research. I said, sure. With me, yes, okay. I'm going to identify a problem and you're going to run it. And she said, fine. So what did I do for Diane? I had a Muskingum-Gunch nonlinear model, numerical model, Fortran, of course. At the time, that's all we did. We started working with PHP in the year 2003. And this is 1983, so 20 years earlier, we were doing Fortran. We were not doing Excel because Excel did not exist in 1983. Fortran was the method of choice. Okay, so I had a Fortran program, nonlinear waves, Muskingum-Gunch, and I said, I'm going to give you a whole lot of cases and you're going to run them. And I'm interested in finding out if this wave steepen, and if so, how much. And if they don't steepen, I'm interested in finding out if they flatten out. Because we were talking about the steepening or the flattening out. Remember, I already heard or learned that some waves do not steepen. So in other words, we're talking about the negative kinematic shocks. This is a shock on the opposite side. It never happens, okay? It does not steepen. So she said, fine. So she did this work for us. I don't know how many, 100, 200. We usually consider a heck of a lot of tests so the message will be clear, if any, if there is a message. So then we analyzed, and this took a while because when you are doing something new, it's not easy. It's not like it's over there. You got to think about it and toss it around a while. So it took us about a year to come up with what's in the blue here. What you see in the blue in there looks simple, but it took us about a year to do it. Don't forget we didn't know when we started, okay? So first, in the blue, when is the kinematic shock going to happen? First, when the wave is kinematic as opposed to diffusion. So a diffusion wave is not going to have a kinematic shock, period. That's it. Because the diffusion is counteracting the shock tendency. Diffusion is a mechanism acting to oppose the nonlinear steepening tendency. The more diffusive or dynamic, for that matter, a wave is, the less kinematic, and therefore the less the steepening tendency. So only a wave that is kinematic will probably diffuse. It doesn't have to, but it has to be kinematic like a first condition. Second, and we know when a wave is kinematic, by the way. Now we know. Second, there's a low base to peak flow ratio. That was very important. We figured that out. What's a low base to peak flow ratio? What is a peak flow ratio, base to peak flow ratio? It could be 2, it could be 10, it could be 100, it could be 1,000. We had an example when I was practicing in Bolivia in 1989, where we had measured a base to peak flow ratio of 100. In other words, the peak was 1,000. The peak was 1,000 cubic meters per second, and the base was 1. So the peak to base was 1,000. That was the largest I have seen in my practice. Not to say that it's the largest. You can go around the world and figure something out. But typically the base to peak flow ratios are 10%, 20%, on that order. The Amazon has the highest. It's about half. In other words, if the base flow in the Amazon is X, the peak flow is 2X or 2.5X. That's the lowest in the world, for sure. Why? Because the Amazon is the largest river, right? That other river that has 1,000 is the Piraí in eastern Bolivia, in Santa Cruz department. The Piraí has a very unusual situation, geomorphologic and geologic situation, which leads it to misbehave. It's flood prone and so forth. So that's where you get 1,000 to 1 peak to base flow. The steepening tendency, though, which is what we're trying to figure out here, is when the flow is subject to large relative changes, with base flow being only a small fraction of peak flow. In the limit, as base flow approaches 0, that is, in the case of an ephemeral stream, the steepening tendency is greatest. That's it. What is the base to peak flow ratio of San Diego River? Well, when we didn't have the 2 dams, it could have been maybe 5%. But now that we have the 2 dams, it's 0. The base flow is 0 because the water is held by the 2 dams, El Capitan and San Vicente. And now we have San Vicente 2.5 times bigger than what it used to be 30 years ago. We're even retaining more water. We don't let any water, hardly any, let's put it that way, to get into the San Diego River. So that's the story in the San Diego River. But other rivers that are free to flow their waters, that are different, and they present different numbers. Okay. Third, so that we got the peak to base to peak flow ratio is very important. Third, hydraulically wide and sufficiently long channel. Oh, this is extremely important. We figured that out by hundreds of trials. The basin has to be hydraulically wide. The river has to be hydraulically wide. Why? Because the hydraulically wide condition for beta equal 5/3 is the only one that given time will have the tendency to form the steepening. 5/3, that means 5 is greater than 3, 5 greater than 3. So therefore, if you give it enough time and space, it will steepen. 5 will overcome 3, right? That's the way it is. Since the wave is steepening is gradual, a sufficiently long channel is needed to give the shock. So if the steepening is strong, may require a shorter reach. It depends, you know. So here it depends on the actual situation. Like in the case of the Colorado Big Thousand Canyon, where a flood wave killed 139 people in the year 1976, it was a very steep channel, and it was a canyon. And canyons, believe it or not, have actually betas or 5/3. Yeah, because you don't let the water go anywhere. It's in the canyon, right? So the beta is 5/3. The actual beta is 5/3. You don't let it spread. If it spreads, the beta immediately reduces to 4/3 or even 3/3. At 3/3, nothing's going to happen, right? But as long as it remains 5/3 by virtue of it being constrained, it will have a tendency to steepen. Okay, so I say in here precisely what I just said a minute ago. Okay. Conversely, in shallow riverbank situations with rapidly expanding channels that are rapidly expanding their top width, such that the wetted perimeter increases in the same proportion as the flow area, consequently the hydraulic radius remains constant, the steepening tendency is counteracted and shock development is arrested. So in the so-called hydraulically inherently stable channel, you'll never have a shock. Never. Impossible. Why? Because the 5/3 got reduced to 3/3. So which speed of the wave is going to overcome which? They're the same. They cannot be overcome. You cannot overcome one with the other. Correct? Now, fourth, this is interesting because this stuff in here we developed in 1983, and it was in 1993 that we came up with the calculation of the inherently stable channel. We already knew that this could be done, but we had to wait 10 years for Pedro Porras to come through and said, Professor Ponce, I want to do a thesis with you. I said, oh, okay, fine. I got a topic. So that's the way we work. We got the topics lined up for the students. That's the way it should be. Fourth, there's a high fruit number flow. In hydraulically wide channels, high fruit number flows lack sufficient diffusion to effectively counteract the steepening tendency. High fruit number flows lack sufficient diffusion. Therefore, high fruit number flows, the steepening tendency may be promoted to the point where the shock may develop. In other words, if you have high fruit number flows, you will have more steepening because you don't have the diffusion. I don't know if it's as confusing or not, but you can review it again. Hopefully it'll make sense. Theoretically, as the fruit number for turbulent flow approaches the condition of neutral stability, 1.5 of Manning, 2 for Chesi, the shock becomes unstable and the theory ceases to apply. In practice, however, such high fruit numbers are rare in natural streams. So the instability is very seldom encountered in natural streams. But in an artificial channel, you can have it. And that's the reason why the roll waves of Dressler and other people form only in artificial channels, not in natural channels. There's a case in Bolivia where they had a natural channel. They never had a problem with it. Then all of a sudden they had development in La Paz, capital of Bolivia. So they had to urbanize the area. And they decided to constrain the channel. They said, oh, well, this channel is too wide anyway. Let's calculate the flood and so forth, and we're going to do a drainage channel in here. So they did a channel in concrete. The next year, the next couple of years, they had a roll wave in there. We talked about that in open channel flow. Why? Because they increased the speed, they increased the beta. The beta was 3/3, and now 4/3, now 5/3. At 5/3, it becomes dangerous. And there's a long channel, actually, I've been there. It's a kind of a long channel. It's got a few miles, like 10, 20 miles. And remember, you have to have length in order to develop. So therefore, they currently have a problem, which, by the way, I don't believe they have solved yet. I was there 2 years ago, 2.5 years ago, and told them how to do it. They're still thinking about it. They want to develop themselves. You know, that's just the way it is. Um, in artificial, by the way, fixing that problem is not easy. First, you got to want to do it. And I'm not sure that they want to do it. Second, you got to have money in order to fix it because those channels were done 30 years ago. And you have to, if you're going to redo it, then you got to pay monies, dollars or pesos, I guess, of this time, not 30 years ago. So you got to want to do it. And second, you got to have the money to do it. Third, you got to know how to do it or have somebody as a consultant that will help you do it. And they don't need me. They have smart people in there that could do it, or they could read my publications and understand them, by the way. But to my knowledge, they haven't done it yet. They're working on it. They're thinking about it. But these things, they are slow. For some reason, they are slow. Believe me. I've been trying to convince people of the Verdenico number for 30 years, and so far it's been mixed. Okay? So at any rate, the four physical conditions, I already repeated the four physical conditions. The conditions for kinematic shock haven't been identified. The question remains as to whether the kinematic shock is as common in practice as calculations using the Overland Flow would seem to indicate. So what did Kibler and Woolheiser said? Actually, Kibler, his thesis, he said, while the kinematic shock, this is the green box, while the kinematic shock may arise under certain highly selective physical circumstances, it is looked upon in this study as a property of the mathematical equations used to explore the overland flow problem rather than an observable feature of this hydrodynamic process. What is this? I'm sorry, Kibler. He's beating around the bushes. He doesn't quite really know what he's saying because we already exactly defined how exactly does this happen. Given enough time and or space, and given those four conditions, the steepening will develop. And the kinematic shock will develop. The so-called kinematic shock will develop. So what I hit with them was correct. When they did the calculations and they stressed and they talked about it so much in 1955, talking about it from the mathematical standpoint. The shock is an uncommon occurrence in natural channels. Dynamic, we got 5 minutes here. We're going to finish here. Dynamic extension to kinematic waves. Oh, this is interesting. Fascinating. When I wrote this paper, I decided to put this section 9 in there. Dynamic extension to kinematic waves. And of course, I got back from the reviewer saying, oh, this is too much, Ponce. You already did a great job up to 8. Why don't you drop chapter 9? Drop it. We don't want it there. I said, no, I'm going to put it in there. Well, they were not forcing me to do it. They just said, we suggest that you should drop. This is another subject. Write another paper, right? But no, I said, no, I'm going to put it in there. So for the first time in 1980, when was this done? 1984. I came up with the Doog, right, which expresses it this way. So Doog came up with 9 in 1958-60 through his mathematics, the linear. We already talked about this equation, okay? But we had to wait until 1973 and then later 1982, I believe. I believe 82 should be in here. I'm not sure why it's not there. But the equation 10 was presented by Doog and his associates in 1982. In 1982. And remember, this paper is only 84. And finally, for 11, we wrote it this way. Okay? So we finally said that, I'm sorry, this is paper, I'm confusing the issue here. This is not a paper in 1984. The paper 84 was the blue box. This is a paper of 1991. So in 1991, I came out and said, Doog's equation is incomplete. His collaborator's equation is incomplete. The real equation is this one over here, 13. You can replace the numbers in here and find out. So I gave credence to Verdenico. I said Verdenico is very important because he shows up as the appendix of Hayami that was not explored by Hayami because Hayami did not get into inertia. When Doog and Verdenico, no, when Doog gets into the inertia, we get the Verdenico in there because Verdenico did not develop this equation. Verdenico just developed the V over here. So we put it together. We put together the work of Duke and his collaborators, the Polish gentleman, Kuntzewicz, I guess his name is, and all the others, Conch, Vedernikov, everybody, into this equation 13, which was written in 1991 extensively. And this is one of the next papers we're going to read this week, I believe, this week or next week. So this is a fundamental equation. How good it is in practice? And the answer is mixed. In my opinion, you should put it in there always. However, don't be surprised if for the regular channels, 0.2, 0.3 doesn't make a whole lot of difference. It only makes a whole lot of difference when the fruit number starts getting high, like 0.7, 0.8, 0.9. At that point, it starts bearing upon on the calculation. So since it's so easy to put it in or put it out, we just put it in because that is the complete. That amounts to putting inertia into the problem of overland flow. So it's not diffusion anymore. Complete diffusion is only this. With this, it's already inertia. It's already dynamic, on the way to being dynamic. It's not dynamic of Fred because Fred's is uncoupled and numerical. This is coupled and theoretical, right? So there are different things in here to be considered. Finally, summary and conclusions. I got 2 minutes in here. I can skip this part because I already reiterated extensively. We know when the kinematic shock occurs. We know that the kinematic waves has an error in there, and that we have to calculate through the procedure developed by Conch. We know that kinematic waves can be improved by extending it to the realm of diffusion waves, and that thereby ending up with the Muskingum-Conch. We know the applicability. We know the distinction between unit hydrograph and kinematic and overland flow. There's apples and oranges, completely apples and oranges for the same thing. And we finally, the dynamic extension is reviewed with a view to the future. Parallel to this work that we published in 1991, I believe, we published the complete answer to this equation, which we're going to read subsequently. I believe at the end, next time we meet. Okay, so with that, then I've exactly used all my time in here. So what I'm going to do in the minute I have is remind you that you should work on your projects, selection your projects. I have the time this week to help you out if you have any doubts about what to do. But you must do this between now and next Monday. Well, thank you very much for your attention. And right now, if there are no specific questions about it, I'm going to stop the share. Questions? We already exceeded our time. So then we'll see you Wednesday, and we'll continue on the 4 other papers that we have. I wanted to spend a full period on this one because this one is the base of the others, and it is important. The others will be a little lighter and repetitious too, by the way.